Hi and thanks for coming to the session. My name is Martin and I'm a third-year PhD student from Southern University in Germany. Today I'd like to present our work on investigating noticeable hand redirection using physiological and interaction data. However, this work would not have been possible without the support of my amazing co-authors Cora, Tony, Tobias, Maurice and Antonio. VR illusions are an effective way to improve the haptic resolution of VR experiences, reaching from techniques such as redirected walking or change blindness redirection all the way to hand-based illusions, which are the focus of this work. Here are a few examples of different VR illusion techniques, such as haptic retargeting, allowing a single physical proxy object to act as a stand-in for multiple virtual objects. But there exist many more. They all have one thing in common: they offset the position of the virtual hand from the position of the real hand. And if you have not gotten the chance to try this yet, I would strongly encourage you to do so, because up to a certain extent it remains unnoticeable that your virtual hand is being offset, which is quite impressive. However, how much discrepancy can be introduced without a user noticing remains unclear. As a result, there has been a lot of research investigating this, reporting so-called detection thresholds for the possible discrepancy, such as by Zenner and Krüger. However, it has also been noticed that these thresholds are not fixed values. They depend on several variables or parameters such as task complexity, realism, or movement direction. Here you can see X and Y seem to be quite different. In addition, thresholds also appear to be highly individual. To determine such detection thresholds, researchers use psychophysical methods, such as this interleaved staircase procedure. In a nutshell, we change the variable of interest, such as movement trajectory. Then we let participants perform a simple movement, either increase or decrease the virtual real hand offset, and ask participants whether they notice the manipulation. Afterwards, we compare both sets of thresholds to determine potential differences. There exist many valid questions and concerns about the generalizability of the results. For example, what if you change how you hold the proxy? Or thresholds most likely differ from one day to another, perhaps due to fatigue. Also, you calibrate them at the beginning of the VR experience, but after, let's say, 2 hours, they might have increased drastically because your tolerance changes. So the bottom line is, unnoticeable illusions are effective, but there exist sheer endless variables that may or may not affect the possible discrepancy. Therefore, our long-term vision is to establish an approach that lets you automatically tailor illusions to an individual's perceptual boundary in an on-the-fly fashion. And what I mean by that is that the system would monitor the user and detect if we approach the current limit of the possible discrepancy, giving the VR experience, and adapt if necessary. In the first step, we investigate the potential of physiological and interaction data for this purpose. Here our main objectives were: are physiological responses triggered when experiencing a noticeable illusion? Can interaction data reveal a noticeable illusion? And finally, do humans adapt to noticeable virtual real hand discrepancies? To do so, we designed an experiment that consisted of 2 parts. In the first part, we computed participants' individual detection thresholds using an interleaved staircase procedure. As a result, Part 2 of the experiment was tailored to each participant. We had 4 study conditions: 2 times baseline, steady, and mixed. In the baseline condition, no hand redirection was applied. In the steady condition, participants executed all movements with noticeable hand redirection. In the mixed condition, we randomly switched between noticeable and unnoticeable hand redirection. In this first iteration, our goal was to distinguish between these conditions, but not between single trials. We recruited 22 participants, 9 of them had never used VR before, and the experiment took about 90 minutes. We used a simple hand redirection task, asking participants to move an object to the target location while changing the gain factor. We collected EEG data using a 32-channel headset from Brain Products. Skin conductivity, respiration, and heart rate variability were monitored using a Plug's biosignal research kit. Further, we tracked several interaction parameters such as movement profiles and collected participants' subjective responses for analysis. For more information about the filtering and the post-processing pipeline, I would like to refer to the paper. Next, I will present a subset of our results. So first, we will take a look at the EEG, analyzing error-related potentials. Here you can see a typical ERP mean curve of a single participant with strong error negativity. Notice that, although weaker, even the baseline conditions show error negativity. Next, we extracted peak error negativity for all participants. We can observe two things. First, the magnitude of the peak negativity in the mixed condition was significantly greater than in any other condition. Second, all conditions showed strong peak negativity at the beginning of the condition, even the baseline, suggesting that this phase is perhaps used for initial self-calibration. In the baseline and the steady condition, the error negativity decreased, whereas in the mixed condition, it remained strong. After the first 4 to 6 trials, the steady condition, with noticeable hand redirection, was indistinguishable from the baseline, suggesting quick adaptation. Similarly, when looking at the transition points from the ballistic movement phase to the correction phase, we found significantly earlier transition points between the baseline and the mixed and the steady condition, both in terms of distance and time. However, this was only true for the first 4 to 8 trials in the steady condition. Afterwards, it was again indistinguishable from the baseline. This is in line with our EEG results, suggesting that participants may quickly adapt to the offset. Our analysis on the number of skin conductance responses showed a similar downwards trend in the steady and baseline conditions compared to the mixed condition. Here, most SCR peaks occurred in the first half of the condition. However, we could not identify significant differences between conditions. Finally, we ran an exploratory data analysis on the extracted RSP and ECG features, because based on the related work, we were unable to formulate clear hypotheses prior to the study. Thus, we discussed promising indices based on our PCA and effect size analysis. In addition, we contribute a dataset with EDA, ECG and RSP features that together with our exploratory data analysis ought to inform future hypothesis-driven testing. However, one thing we learned was that individual responses seem to be consistent but differ substantially. In summary, we found that conditions with noticeable hand redirection significantly differed in error negativity and showed much shorter ballistic movement phases. Next, participants can adapt to discrepancies after 4 to 8 trials, which was suggested by several of our collected measures. Finally, we provide a first investigation of EDA, RSP and ECG features to detect noticeable hand redirection. Thank you very much for listening.